Thank you. Good morning. Let's make sure this clicker works here. Good, it does. My name is Ed Godlewski. I'm Vice President of Fluor Corporation. I'll be introducing you to our company and the important OR work that has brought us here today. Part of my role in managing the ongoing use of that work here at Fluor. My former colleague, Greg Lee, will describe to you the challenging setting that inspired us to implement this work. Greg led the first years of implementation for Fluor and now works with Ken Cooper. Ken was scheduled to describe for you the technical solutions this team developed on the issue that is so central to our business's performance. Unfortunately, Ken has come down with pneumonia and can't attend. Also joining us today is Peter Oosterveer, President of Fluor Energy and Chemicals, our largest business group. Peter will offer his executive viewpoint on what the new capability means to our business and to Fluor's clients around the world. It will help you to know a bit of the background about Fluor. So in order for you to appreciate the importance of this analytical tool, let me describe our business. Fluor designs and builds many of the world's most complex projects, from power plants to pharmaceuticals, infrastructure to chemicals, oil refineries to gold mines. We do this in locations around the globe, from the oil sands of Alberta to the mountains of Chile, to the deserts of Australia, and throughout the Middle East. The projects range in size up to many billions of dollars. For all of you who have been involved in a large, technically complex project, it may not be surprising that one of the biggest challenges is controlling project cost and schedule performance in rapidly changing conditions. To help us do just that, we had implemented a simulation model-based system that has transformed our management of projects and changes. We tailor a systems dynamic model to each major project and use the model to quantify and diagnose the future impacts of changing project conditions and to test ways to avoid those future costs. In doing so, over the first 5 years, we've identified over $800 million in savings for our company and our clients around that world. To put that number into perspective, I would say that if you look over here, we last year had $680 million of net income on $22 billion in revenue. We currently have a backlog of about $26 billion worth of work, and we have 36,000 employees worldwide. Fluor is number one in Fortune Engineering Construction's category for engineering, number 111 in the Fortune 500. And Engineering News-Record ranks Fluor number one among the 100 top design build firms and number 4 in contractors. Of course, we aim to sustain and improve that performance. Vital to Fluor's success is the ability to execute successfully large, complex projects around the world. The system we describe today is key to that success. Here on video, to describe the business importance of what's been achieved, is Peter Oosterveer, President of the largest business group in Fluor. That's our energy and chemicals business.
Hello, I'm Peter Oosterveer, President of Fluor's Energy and Chemicals Business Group. I'm very pleased to speak with you about the benefits Fluor is achieving through our implementation and use of the project simulation analysis tool and how it solved such an important problem for us. As a leader in our industry, Fluor decided 5 years ago to deploy a management science-based breakthrough in how we manage the impact of changes on the projects we execute for clients worldwide. The use of this new tool has improved our own business and dramatically reduced costs for our clients. Changes occur on most projects, as many of you surely will have experienced. On our large upstream petrochemical and refinery engineering and construction projects, changes take place throughout the life of many projects. Predicting the full cost and the delayed effects of these changes has always been difficult in our industry. But we saw that it was important to foresee those impacts and to go beyond just prediction. We were also determined to find more effective ways to reduce the impacts before they could cause cost and schedule performance problems on our projects. We combined the groundbreaking analytical work here with worldwide management training and we have successfully used the tool on well over 100 projects. What capability does it provide to Fluor? It provides us and our clients the ability to predict quite accurately the quantum of future impacts that will be triggered by a proposed change. It helps us understand why and when those impacts would occur on the project. And it enables us to test and identify methods for reducing the cost before the costs occur. The many business benefits such a capability brings are significant for our company and our clients. First, advanced quantification of the full change impacts enable our project teams and clients to determine if a change or set of changes is an economically correct decision to take. With this advanced knowledge of the full impact, sometimes the better decision is not to implement the change. If the change is implemented, we do so with a far better understanding of the future impacts on cost and schedule than the industry has ever had. Imagine what the benefits are to us and our client relations when we can help avoid late cost and schedule surprises on projects. Second, the advanced diagnosis allows our managers to formulate and consult with our clients on what action can be taken to reduce the impacts. In this arena of benefits, we sometimes find better processes in implementing the changes or more efficient ways to staff the work or to schedule the project. And thus the tool helps identify cost versus schedule trade-offs for our clients in what we believe is a high value-added element of our services. On just the quantifiable aspect of these benefits, we have identified hundreds of millions of dollars in savings for our projects in what is clearly a win-win for our company and for our clients. I've personally seen it work with success on our clients' projects. Using the tool improves engagement and relations between us and our clients, who understandably welcome the ability to avoid cost and schedule problems, and instead to achieve cost savings. And I can tell you, it is obviously a far more satisfied client who can see the identified savings on their project. Third, we have literally transformed the mindset that had existed in the industry. It used to be that the industry handled these changes retrospectively, sometimes even in outright disputes. We have changed that to a proactive mindset with our management teams, one in which the cost and schedule impacts can be foreseen and mitigated or avoided entirely. I cannot emphasize strongly enough just how important a difference that makes in our business. For example, during one European project, the client took our analysis to their corporate management to replan the entire construction schedule, saving $23 million.
Good morning. My name is Greg Lee, and as Ed pointed out, we are delighted to be here in front of you presenting what we think to be important work for Fluor. My challenge is to do two things. One is to cover the slides that I had originally planned to cover, and then figuratively step into some very large shoes. Unfortunately, I don't think I'll be able to fill those shoes, but I'll do my best in covering the material that Ken was originally expecting to cover, which talks about the methodology itself. So let's get started. Historically, there have been several significant challenges in achieving the kind of results that Peter just described. First and foremost, because the projects that Fluor and others in the industry conduct, namely they are one-off, one-of-a-kind projects, change is inevitable. Changes that occur due to late information, delayed decisions, schedule changes. On some projects, that impact can result in as much as 20 to 30% of the total project cost. Secondly, much of these impacts arise from what is becoming known as secondary impact, oftentimes referred to as ripple effects, disruption, cumulative impact, productivity loss. It's the effect of introducing change under conditions where, if those conditions are not favorable, the cost of introducing that change can vary substantially depending on when and how it's introduced, regardless of the label used to describe this impact. It is typically underestimated, under-recovered, and appears only late in a project in the form of a surprise. Taking preventative measures is virtually impossible if you've already spent the money to accommodate that change. So what happens when a project costs millions, or in many cases tens of millions, more than planned or contracted? You have unhappy clients. You have legal disputes that often arise. How do I know this? Because I ran Fluor's claims group for over a decade. It is not a fun business. That part of the business is not a fun part of that business. Why does this exist? In many cases, the practice of project management in certain aspects is reactive. The perception is that changes are inevitable. The project will cost what it's going to cost. Our job is to make sure we account for it, estimate those costs as they occur, and fight over the responsibility for those costs at the end of the project. What operations research has enabled at Fluor is a proactive approach, where issues are anticipated, the potential impacts are mitigated to control their future effect on project cost and schedule. And these are not in esoteric areas. They're in mainstream aspects of project management, such as scope additions. Sometimes the scope of projects has to change, whether it be an increase in scope or a deletion of scope. It is the source of significant consternation in terms of accurately pricing the ultimate cost of incorporating scope during the course of the project. Most projects go through a preliminary, or in the capital projects vernacular, front-end engineering design phase, where scope is defined. There is a constant tension between how much scope definition do I have the opportunity to create before I get into detailed design, given what my schedule objectives are. Engineering work schedules. You get into the project, for some reason, maybe the product value has changed over time, and the client, for whatever reason, wants to evaluate the value of accelerating the project. Construction work schedules. The site is a challenging site. Engineering is having difficulty progressing. We want to get to the site so we're ready to build. Mobilizing a very expensive force of people that can number in the tens of thousands on very large projects is a very expensive endeavor. Making sure they're used efficiently at the right time is a challenge. Many large projects rely on major equipment manufacturers for data that is required in order to complete the design. The timeliness of that data, decisions that bear on changes that bear on the timeliness of that data are critical to efficient project execution. A project gets behind. The natural response is throw people at it. But if those people can't use the data that's available to them effectively to be efficient, then all you're doing is expending money with no benefit. That analysis heretofore has been extraordinarily difficult to do with transparency. And finally, does the timing of key decisions make a difference? Well, intuitively, clearly it does. But how do you translate that into an analytical process that can be used by project participants to make informed, insightful decisions about avoiding unnecessary costs? This is the bread and butter of the technique. These are the tools of the technique, if you will, that have been employed at Fluor. Let me state it a little differently. This is a graph of the staffing plan on a real live project. We will call it Project X to protect the innocent. This project ended up expending labor in this way. Nearly 100% increase in the labor needed to complete the project. Why? Because in some ways, changes that occurred early in the project didn't manifest their consequences until later in the project. And if the money has already been spent, if the project has progressed to that point in time, there is no opportunity to mitigate those costs that would otherwise have been unnecessary to expend. That's the challenge that Fluor faced. It's the challenge that the industry faces, and one that we were bound and determined to address. Unfortunately, there were more challenges. One is we didn't have the opportunity to look retrospectively. This approach had to be prospective, to be able to, in advance, look at what would happen if we did something different. To be effective in that, the technique had to identify timing. When is it too late to do something? Causation. If I don't know what's causing the problem, then how am I going to develop mitigating strategies to avoid that problem? And it's not just in construction. We're not talking just about the placement of steel and pumps, wire and cable. Events that take place during engineering have huge leverage on the efficiency in the field. And when you have literally thousands of people in the field all waiting for something to do, you can't afford not to feed them the necessary design documents to allow them to do their work. What's the difference in effect between one large change and the so-called death by 1,000 cuts? And to bring true systemic benefit, the approach has to be usable broadly, it has to be quickly employed, and it has to be accurate. People have to believe in the results. So that paints the picture of the challenges that we confronted. And now I'm going to take that figurative step that Ken Cooper would have taken at the time and talk a little bit about the technique. We have a three-part analytical solution that was developed. The first part was the development of a system dynamic model of projects. Many have tried, many have failed. And we'll talk a little bit about why system dynamics is particularly adept at this approach. We'll also spend a little bit of time talking about the tools necessary to rapidly tailor the model. It's one thing to have the ability to accurately simulate a project, but if it takes you 6 months and several $100,000 of very highly skilled time to get that model, the project's moved on. And it had to be deployable to projects and usable by people who were not system dynamic modelers. Also a huge challenge. So why is system dynamics particularly adept at these challenges? Well, as you know, system dynamics is a methodology and modeling technique for analyzing complex systems. It's rooted in engineering control theory. The method has been used on numerous applications in organizations, industries, and particularly in complex projects. Why is it particularly adept here? Because it deals with cause and effect relationships. The effect of one factor on another. And in particular, it deals effectively with time delayed and effects that are nonlinear, as the effect of, for example, overtime on productivity. The second feature of system dynamics that makes it so appropriate here is that it accommodates the existence of feedback loops. Feedback loops, as you know, can be corrective or self-reinforcing. For example, in one instance, more overtime increases progress, thereby reducing the need for additional overtime, a corrective influence. But if you use it in excess or for sustained periods, overtime lowers productivity through fatigue, slows progress, and thus increases the need for overtime. And so the approach has to be flexible to accommodate these nuances of the way things really happen in the real world. So our objective is to take and develop a model that can accommodate the cause and effect relationships as described by equations embedded in the model. We then, if we accomplish that, can simulate the behavior over time and accurately represent a project plan. If we cannot accurately represent the project plan, then we cannot argue that it will respond as the project would respond. And so the objective is to develop great fidelity between the project plan and the simulated. And if you're able to do that, is when the fun takes place. That's when it starts, because then you can subject that simulation to a variety of what-if scenarios to determine whether the consequences of an event will be good or bad to the project. In other words, what we needed on Project X was the ability to foresee and avoid. But first we needed to understand what was going on. So we went and talked to the project team. And through the course of the project, they described that they had a tranche of work to get done. They applied people and productivity against that tranche of work and expected work to get done. The formulas for representing that in a model are above this very simple linear representation of how work is supposed to get done in a project environment. But we kept hearing from them that our productivity was impacted. And when we asked, what do you mean by that? We got a variety of different answers. So we thought it best that we go look at the data. And when we looked at the data, we saw the project team did in fact issue initial drawings as they had planned to issue those drawings. But then one day in a review meeting, one of the process engineers sat back and said, you know, I've got a really good idea, I think, about how to improve the design that will save cost, improve the schedule, and it does require that we do a fair amount of rework, but it can be justified. So naturally, it was adopted, and they issued many of the drawings again to reflect this great idea. Over the course of time, there were other great ideas. There were some errors that were found, and unfortunately, additional work was required. But at the end of the day, the engineers had the eloquent solution, which is what engineers are trained to get, right? It just took a little longer and cost a little more than they had anticipated. Well, our linear model of how work gets done in projects doesn't accommodate this. It fails to address this fundamental issue about the iterative nature of design projects. So we have to go back to the model, and we have to add to it a feature that talks about and deals with the rework cycle. And we're going to introduce this notion of quality. And quality is a simple notion that just measures the fraction of work that isn't subject to subsequent rework. When work is done, it's really done, okay? But unfortunately, not all of it gets done and stays done. And because in a complex project, there is dependent technical work that is impacted as changes propagate through a project, that there is a tranche of work, the insidious, undiscovered rework, that only raises its head at the most inopportune time, typically at the end of a project. And so to make our model reflect what actually took place on the project and reflect reality, we need this rework cycle that acknowledges the existence of both known rework and yet to be discovered rework. With that, we could explain much of what was going on, but we needed to place it in the proper context. So I'm going to shrink this simplified version down. And as I go through this, I'm going to ask you and the audience, judges, think about a project that you've been on. It doesn't have to be a capital project. It could be a software development project, an aerospace project. It could even be a home remodel project, okay? And I'm going to add some features to it that see if some of this strikes a chord. We'll introduce change. And immediately we know that we have more work to get done. We know we have rework to do because we have to go and revise work. We know that our expected hours of completion will be higher because we have to go do that work. And typically, when change occurs, there's a question about, well, do we extend the schedule to accommodate that to use the most effective people? In most cases, the decisions from clients and contractors is, the schedule is sacred. We're not going to change the schedule. So in the face of not changing the schedule and in a tight labor market, you effectively must deal with this through the use of creating more people, and that is by the use, use of overtime. We all know from industrial engineering that the use of overtime has some measurable effect on quality and productivity. Eventually, hiring brings in people from the outside, and if it's in a very intensely competitive labor market, those people arguably have lower skills. If the change is significant enough to change some of the vendor data, the dependence on vendor data requires the engineering staff to work out of sequence or make assumptions, also impacting quality and productivity. And eventually, if pressure on schedule, pressure on budget, continued exposure to rework strikes the design staff, what do? They sell the hell with it. Life is too short. I'm working long hours. I'm getting no credit for this. I'm going to go work at XYZ because they got a nice 4-day-a-week project and they pay as well. I'm out of here. What does that do? It creates turnover, and we start creating that self-reinforcing feedback loop that we talked about earlier. Now, when more time available, I'll usually query the group as to whether anyone has ever seen this. I'll give you the answer. In presenting this to several thousand people, no one has ever said, no, Greg, that's alien to me. I've never seen that. So I'll ask you to accept on face value that we have a diagram reflecting the influences of these parameters on the way work is conducted in a project environment, which gives us a concept of explaining what's going on. Now we must work to get a model, a functioning model. How do we do that? Well, those influences are reducible to equations for, in this case, the rework cycle, productivity influences, staffing influences, which are a function of work to be done, work completed, and the time remaining. And as a consequence of working the concept with the reduction to equations, we have satisfied the creation of an underlying base model of system dynamics accommodating the cause and effect nature of it, feedback loops, and the time delayed, our nonlinear consequences of those influences. Our next challenge in this 3-step protocol is to make sure that we can tailor the simulation to reflect unique project circumstances. It is unsatisfying for a project team to use a model that is an average project model because projects are different. How do we get there? We start with a core model. We want to achieve a situation where the simulation will replicate the underlying plan that the project team adopted at the beginning of the project. And to do so, several steps had to be developed. Several new steps had to be developed, including the ability to create to populate a project model that could then be converged with the actual project data. That was done in several steps. First, there was an interface created where we actually embedded the project plan. I shouldn't say we. It was designed so that the user could embed the project plan into the simulation. Secondly, through extensive interviews, the use of reference standards, we assured that the underlying assumptions that were used to create the original project plan were also translated into the simulation model. Third, in order to converge the simulation model with the actual plan, we employed a series of hill climbing algorithms to make that convergence. At the initial simulation, of course, you're going to get displacement between the actual plan and the initial simulation through the use of a very slow algorithm here, subjecting it to the hill climbing algorithms. We were able to, and if you look at the graphs on the right-hand side of the screen, you can see over time and iteration that they actually do converge to the point where at the end of that process, we end up with remarkably close approximations between the simulation and the actual plan. What does that enable? That enables us now to have the fun. That enables us to sit with the system, subject it to what-ifs early enough in the project to be able to identify consequences that we want to avoid. But it's got to be done by project participants because Fluor wasn't about to hire a bunch of system dynamicists and have them run around the company doing things that people didn't understand. So how did we accomplish that? Primarily through a user interface where people took data that they were used to dealing with. How many hours are we going to inject as a consequence of this change? When are those hours going to be expended during the course of the project? How much of the design does this change impact so that we know how much to to inject into the simulation model. The tool returns a number of answers. In this particular case, real project, there was 12% additional work injected into the project at a given time. That resulted in a 30% increase to project labor arising from the inopportune introduction of these events and driving productivity to a point of incurring those extra costs. The tool responds with a comparative analysis of those influences that are driving that productivity loss. In this case, it was the existence of continuing change in the engineering that was driving that problem, and so that develops the opportunity for the user to develop hypotheses on how to approach reductions in the amount of change in engineering. Was it endorsed? First 5 years, the applications doubled every year. Why? Because we were then able to go to a client, in this particular case, a client where cost was paramount. It was absolutely important that we remained within the cost targets of the project, and they asked, could we accelerate the project and remain within that? The analysis showed that we would incur a significant increase in engineering labor, but that's not sufficient. We need to know why that's going to take place. As a consequence of having to bring in more, less experienced people, as a consequence of the vendor data being less available and therefore supporting the schedule, as a consequence of a nonlinear increase in the amount of revision effort that would take place in the project, we get a picture and a scenario about why this is not a good thing to do. Knowing that it's a cost-sensitive project, the analysis went on to look at, well, what would happen if we were to relax the schedule a little bit? As a consequence of that analysis, this is the example that Peter mentioned in the video, where there was a $23 million savings from the plan, which would have been even greater had they chosen to accelerate the alternative. So, do real projects use the technique? Let's talk about a couple of examples. The classic scope addition. On this particular project, it's a mining project. There were scope additions that were necessary. Traditional estimating techniques would have overlooked about $10 million in cost. You might say, well, gee, that's good for the owner. This is a reimbursable cost project. And so that $10 million was going to get paid one way or another, and it would have popped up at the end of the project, causing lots of surprises. Because they knew that expense was there, they did further analysis, and were able to reduce that cost by $2 million because they knew it was coming. Preliminary engineering readiness. This is the scope definition phase that leads to detailed design. On a turnaround project, that's a project where the plant has been taken down and out of service so maintenance can be done. Every moment that that plant is not operating is losing the client money, and so schedule is really, really important. Client wanted to optimize that situation through the use of the analysis, was able to reschedule the work and reduce the cost by $34 million. Staffing levels. This is the classic case where the contractor was asked to accelerate staffing in order to expedite the engineering effort. The cost of that was quantified. An alternative plan was developed, and this refining project in Europe, $25 million was avoided as a consequence of taking an alternative plan to the one originally contemplated. Does the speed at which design changes are approved make a difference? It absolutely makes a difference, but quantifying that is extraordinarily different. In this schedule-sensitive project, everyone was on board with the need to approve quickly. The problem was that the processes and procedures necessary to do that did not permit that. So the project team calibrated the amount. There was a $10 million opportunity. They actually changed their internal procedures to expedite the review of that process, thereby being able to achieve that $10 million loss, that $10 million savings. Construction work schedules. I have two examples to share with you. One has to do with a very unique opportunity where there were two projects, two very modest projects working in parallel. One project chose to employ the tool to analyze the relationship between when design was mature enough to support field activities so that they would mobilize at the opportune time. The other one chose to use more traditional measures. The project manager for the one that employed the tool, his opinion, his representation was that mobilization went much smoother and the project realized a $1 million savings as a consequence of that optimization. The second one was a project that was incurring a significant change history. And there was a desire, obviously, to seek lower cost. Based on the analysis of various schedule scenarios, the client actually chose to implement one of those scenarios, rescheduling construction and lowering the cost by $23 million. We could spend much more time than I have with you today talking about the 100+ applications. When we do an arithmetic total of those hard dollars, monies in someone's pocket that didn't get spent, whether it's in Fluor's pocket or our client's pocket, since 2006, that number is in excess of $840 million. Impressive? Am I enthused? Absolutely. But what I'm even more pleased to report to you is that an association of the world's foremost contractors, known as the Engineering Construction Risk Institute, Fluor chose to expose the technique to that body. They weren't going to take Fluor's representation on face value, so they commissioned, through Texas A&M, a comparative study of the approach. And as a consequence of the comparative study, have adopted the underlying methodology as industry best practice within the engineering procurement construction industry. I'm enthused. For those of you that represent the operations research management science community, I want to convey to you my personal thanks for having the tools available to solve a problem that has literally existed since the pyramids. The pyramids were built. There was an EPC contractor that built the pyramids. Okay? They had change issues. They didn't have the approach, and it is the OR community that has brought that solution. There are also business reasons to rejoice, and I think Peter probably does a better job at conveying those to you than I.
From my nearly 3 decades in the industry, I can tell you that this tool's advanced information and what-if analysis result in better decisions and better project outcomes, better business outcomes for us and for our clients. The use of this tool has enhanced Fluor's ability to deliver challenging world-class projects on time and on budget. Thank you for considering this tool for the Franz Edelman Award.